Hey there, welcome to TechX Bytes. In this module, you'll learn how Docker revolutionizes app development and deployment using containers. We'll walk through real-world challenges, how Docker solves them, and what happens behind the scenes. By the end, you'll be ready to build and run your own containerized applications. Let's get started. Docker is an open platform for developing, shipping, and running applications. It allows developers to bundle their code and dependencies into containers, lightweight, portable units that run the same anywhere. It's fast, consistent, and eliminates environment-related bugs. A major pain point in software development is inconsistent environments. What works on a developer's machine often fails in staging or production due to different tools, versions, or configurations. This causes bugs, delays, and frustration, especially when every environment is manually set up. Docker solves environment inconsistencies by using containers. A Docker container packages your app with everything it needs, the code, runtime, libraries, and dependencies, so it runs the same way on every machine. From your laptop to production, it's consistent and reliable. Docker relies on key features of the Linux kernel. Namespaces provide isolation, cgroups control resource usage, and union file systems allow efficient storage through layering. On Windows or macOS, Docker runs these features inside a lightweight Linux virtual machine. To get started, we need to install Docker. Visit the official Docker website and download the installer for your operating system. Follow the instructions to set it up. If you're on Windows or macOS, Docker Desktop will handle everything for you. Once the Docker is installed and running, next we'll verify the installation. To verify Docker is installed and ready, this command shows the installed Docker version. If you see a version number, you're all set. If not, check your installation steps again on docker.com based on your operating system. Let's run a simple command to see Docker in action. The docker run hello world command pulls a small image from Docker Hub and runs it. If you see hello from Docker, congratulations, your Docker installation is working perfectly. This image is designed to demonstrate that Docker can pull images and run containers. Now let's break down what just happened. When you ran Docker run hello world, it started looking for the hello world image on your local machine. Since it wasn't found, Docker pulled it from Docker Hub, which is a public registry of Docker images. After downloading, Docker created a container from that image and executed it. The container ran the code inside, printed hello from Docker, and then exited. This is the basic life cycle of a Docker container. You know the best way to learn anything is by doing, so let's create our first Docker project. Let's create a new directory for our first Docker project. This will be our workspace where we build and run our containerized applications. We'll call it My Docker App. Navigate to your terminal and run the commands shown. This sets up a clean space for our app files. Here's our sample app, a simple Flask web server that responds with hello from Docker when accessed. Nothing fancy, but perfect for learning Docker basics. In case you are new to Flask and are interested in learning more, click on the eye icon in top right corner. We've created our app, PyFile. This Flask app listens on port 5000 and responds with a friendly message. It's a great starting point for our Docker journey. Every Python project needs its dependencies listed. This file tells Docker exactly what packages to install. Here, we're using Flask version 2.3.3, which is perfect for our simple web app. This way, Docker knows how to set up our environment correctly. A Dockerfile is a set of instructions for building a Docker image. This one starts with a base Python image, copies our app files into the container, sets the working directory, installs dependencies, and finally runs our app. It's like a recipe that Docker follows to create our app's environment. If you're new to Dockerfiles, don't worry. We'll go through each part step by step in the next sections. Dockerfile created. Notice no extension. Docker looks for this exact file name. It's like a recipe that anyone can follow. In this step, we build our Docker image using the Docker build command. The T flag tags our image with a name, my Flask app. The at the end tells Docker to use the current directory as the build context, which includes our Dockerfile and app files. Our image is now ready. The output shows each step Docker took to create our image, and the final line confirms it was built successfully. Now let's run our containerized app. The Docker run command starts a new container from our image. The P5000 flag maps port 5000 on our host machine to port 5000 in the container, allowing us to access the app in our browser. After running this command, you should see output indicating that the Flask server is running. Open your browser and go to http://localhost 5000 to see Hello from Docker displayed. Amazing! We've gone from source code to a running containerized app. This container will run the same way anywhere Docker runs. Now, let's dive deeper into Dockerfile instructions and best practices to build efficient, maintainable images. From is always first. It's your foundation. Think of it as choosing your starting ingredients before cooking a meal. Base images are pre-built environments. Slim versions are smaller, but still have what you need perfect for most apps. WRKDIR sets your working directory inside the container. It's like choosing which folder to work and keeps things organized. WORKDIR keeps your app files organized in app, separate from system files. Clean organization prevents conflicts. Copy moves files from your computer into the container. Copying requirements. TXT first enables better caching, smart optimization. Copy requirements first, install dependencies, then copy app code. If code changes, dependencies don't need reinstalling. Run executes commands during image building. Here we're installing Python packages, like setting up your development environment. env sets environment variables that your app can use, like giving your app configuration settings it can read and use. Expose documents which port your app uses. It's like putting a sign on your door, doesn't open it, just tells people where to knock. CMD defines what runs when the container starts. It's like the main function of your container, the purpose it serves. Updated our Dockerfile with best practices, strategic copying, clear documentation, and proper organization. Notice using cache. Docker cache the dependency installation step. This speeds up builds significantly. If requirements, TXT doesn't change, it skips reinstalling packages. ARG creates build time variables that you can use in your Dockerfile. It's like a placeholder that you can replace when building the image. This allows you to customize your builds without changing the Dockerfile itself. Here, we used buildarg to specify a different Python version when building the image. This allows us to easily switch versions without modifying the Dockerfile. It's great for using same Dockerfile across different environments or testing with various configurations. ENTRYPOINT is fixed, CMD is flexible. ENTRYPOINT defines the main command, while CMD provides default arguments. If you run Docker run my app, ENTRYPOINT runs with CMD as arguments. If you run Docker run my app ls, ENTRYPOINT runs with ls as an argument, overriding CMD. This setup always runs Python app, py, but allows different arguments. Default is help, but you can override it. So running Docker run my Flask app uses the default CMD, which is help. But if you run additional flags like port 8080, it overrides the CMD and runs ENTRYPOINT with those arguments. This flexibility is powerful for configuring your app at runtime. Now, let's explore how Docker builds images in layers, which is a key feature that makes it so efficient. Docker builds images in layers, like a stack of transparent sheets. Each instruction creates a new layer on top of the previous one. Notice how Docker reused cached layers for unchanged steps. This speeds up builds significantly. If you change app, Pi, only the last layer needs rebuilding, saving time and resources. User sets the user for subsequent commands. Running as a non-root user enhances security by limiting permissions. It's a best practice to avoid running containers as root, which can lead to vulnerabilities. This Dockerfile creates a non-root user, sets the working directory, copies files with proper ownership, and installs dependencies securely. It's a complete, secure setup for running our Flask app. Volumes provide persistent storage for containers. When a container dies, the data in the volume remains intact. This allows you to create new containers that can access the same data, making it perfect for databases or shared files. Here, we run a PostgreSQL database container with a named volume db-data. This volume stores the database files, ensuring data persists even if the container stops or is removed. The -e flag sets environment variables like the database password. Bind mounts link a host directory to a container directory. This is great for development changes in your code editor reflect immediately in the container. The vpwd/app mounts the current directory to app in the container, allowing live updates. Docker supports different volume types. Named volumes are managed by Docker, bind mounts link host directories, and anonymous volumes are temporary. Each has its use case. Choose based on your needs. Let's now explore how to connect multiple containers together, allowing them to communicate and work as a cohesive application. In modern applications, we often have multiple services that need to work together. Docker makes this easy with networks. By creating a custom network, we allow containers to communicate with each other using their names as hostnames. This is essential for building complex applications where different components need to interact seamlessly. Here, we run a PostgreSQL database container and connect it to our custom network, App Network. This allows our web app container to communicate with the database using the container name WebDB as the hostname. Networking is crucial for multi-container applications, enabling them to work together like a well-oiled machine. In our app, we use environment variables to configure the database connection. This allows us to easily change settings without modifying the code. The os.getEnv function retrieves the values of these variables, providing flexibility for different environments, development, production, etc. When running our app, we pass environment variables using the E flag. This sets DB host to WebDB, allowing our app to connect to the database container. Environment variables are a powerful way to configure applications dynamically, making them adaptable to different environments without code changes. Here's a visual representation of our multi-container application. The web app container communicates with the database container over the app network. The host port 5000 is mapped to the web app, allowing us to access it from our browser. This architecture enables us to build complex applications with multiple services that can interact seamlessly. Our current image is 145 MB. That's quite large for a simple app. Large images take longer to download, use more disk space, and can slow down deployments. We need to optimize our Dockerfile to reduce this size. Multi-stage builds allow us to create smaller, more efficient images by separating the build environment from the runtime environment. In the first stage, we use a full image with all necessary tools to build our application. In the second stage, we use a minimal base image that only contains the runtime dependencies, resulting in a much smaller final image. In this first stage, we use a full Python image to install our dependencies. The user flag installs packages in the user's home directory, which we can later copy to the final image. This stage has all the tools needed to build our app, but we won't include it in the final image. In stage 2, we use a slim Python image that only contains the runtime dependencies. We copy the installed packages from the builder stage and our application code. This results in a much smaller final image that only includes what is necessary to run our app without any build tools or unnecessary files. We've created a multi-stage Dockerfile. This allows us to build our app in one stage with all the necessary tools, and then create a much smaller final image that only contains the runtime dependencies. This is a powerful optimization technique that can significantly reduce image size. The multi-stage build reduced our image size from 145 MB to just 98 MB. This is a significant improvement, making our deployments faster and more efficient. Multi-stage builds are a powerful tool for optimizing Docker images, especially for applications with many dependencies. Layer caching is powerful. Docker caches each layer created during the build process. If a layer hasn't changed, Docker reuses it in subsequent builds, speeding up the process. To maximize caching efficiency, order your Dockerfile instructions wisely is very important. Follow a simple rule: stable layers, like installing dependencies, should come before frequently changing layers, like application code. This way, if you change your app code, Docker can skip reinstalling dependencies, making builds much faster. So like we discussed, we copy requirements, txt first, and install dependencies before copying the application code. This way, if we change our app code, Docker can reuse the cached layer for dependencies, speeding up the build process significantly. Each run command creates a new layer. By combining commands with $, we reduce the number of layers in our image. This not only saves space, but also speeds up builds by minimizing the number of layers Docker has to manage. Now, if want few files to be excluded from the build context, we can use a dockerignore file. Dockerignore works like gitignore. It excludes unnecessary files from build context, resulting in faster builds, smaller contexts. Created dockerignore. Now Docker won't send unnecessary files to build context. Cleaner, faster builds. Alpine Linux is a super minimal base image. It's tiny, only 5 MB, but requires some extra setup for Python packages that need compilation. It's great for production images where size and security are priorities. Dockerignore dramatically improves build performance by sending only necessary files. Less data means faster builds. HEALTHCHCK lets Docker monitor your app's health. Docker can restart unhealthy containers automatically. Docker Scout scans for security vulnerabilities. Regular scanning helps keep your containers secure in production. Cache mounts persist between builds. Pip downloads cache across builds, making repeated builds much faster. Distroless images contain only your app and runtime, no shell, package manager, or extra tools. Maximum security. Our optimization journey, from 145 MB to 45 MB. Each technique serves different needs: multi-stage builds, Alpine base, distroless images, and caching dependencies. Security scanning ensures our images are safe. Like we discussed earlier, ARG allows us to pass build time variables. Here, we use buildenv to conditionally install debug tools for development builds. This way, we can have different builds for different environments without changing the Dockerfile. Built development version with debug tools. Same Dockerfile, different builds for different environments. Production security is multi-layered. Use non-root users, minimal base images, secret management, regular updates, and read-only file systems. Each measure reduces risk and enhances security. Secure by design: non-root user, minimal base image, no cache in pip install. This Dockerfile is ready for production deployment. This is a bad practice. Secrets in Dockerfiles or env variables are visible in image layers forever. Anyone with access to the image can see them. Secrets should never be baked into images. They need external management. Secrets come from external sources like files, environment variables, or secret management services, never baked into images. Read-only file systems prevent runtime tampering. Apps can only write to explicitly mounted volumes, maximum security. Container logs go to stdout/stdir, not files. Docker captures these streams and forwards them to logging systems. In production, logs flow from applications to Docker, then to log drivers like Elk or Splunk. This enables centralized logging, alerting, analytics, and compliance monitoring. It's essential for troubleshooting and performance analysis. Robust health checks test actual functionality, not just process existence. Include timeout and retry logic for reliability. Handle SIGTERM for graceful shutdowns. Clean up connections, save state, and exit cleanly when Docker stops containers. Resource limits prevent containers from consuming all system resources, essential for multi-tenant environments. Docker fits perfectly into CI/CD pipelines. Code commits trigger builds, security scans, and deployments. This automation ensures consistent, reliable releases. Always tag images with specific versions, not just latest. Version tags enable rollbacks and make deployments predictable. Use semantic versioning, v123, for clarity and traceability. Monitoring is crucial in production. Track resource usage, CPU, memory, disk, application metrics, response time, errors, health status, health checks, restarts, and business metrics, users, transactions. Set up alerts for anomalies to ensure reliability and performance. Docker exec lets you debug running containers. Access shells, check processes, view logs essential for troubleshooting. Congratulations! You've mastered Docker from basics to production. You can now containerize apps, optimize images, and deploy securely. If you want to continue your learning journey, explore advanced topics like Kubernetes, Docker Swarm, and cloud-native architectures. The world of containerization is vast and full of opportunities. Keep building, keep learning, and happy containerizing.